counterclockwise. So it looks like a inverted upside down 9. Okay, so take this D and imagine the top hooked to the left in a circular fashion. That would be what's partial. What's called the partial. Anyway, so it's the derivative. It's called the partial derivative. So D of Z with respect to X, for example, is what? So this would be equal to Y. Why? Pardon the pun. Because from the perspective, okay, let's give a comment. From // is Java's way and C++, C++, etc. Way of saying comments. From the variable X's perspective, okay, let me say it differently. Okay. What is a derivative? A derivative is a measure of change, right? What changes? So if you take it, in the last case, in this third equation, in the partial derivative of Z, in the partial derivative of Z, we are viewing the change only with respect to X. We are viewing the change only within the what I just say? And what's the good word? I had a good word. We are viewing the change only within the perspective, within the context. What did I say? The better words. Okay, what word did I use a second ago? Respect to. Thank you. Only with respect to. That's the right way to say it. And thank you. Change only with respect to. Thank you. Wow. With respect to X, but not Y. Therefore, in this context, from X's perspective, that's what I wanted to say. Good. Perspective. Y is a constant, and that is why, pardon the pun, the second equation above is the second rule above is used. It's not a variable; it's a constant, and it's as if it's linear. X times Y. X is the variable. Y is the constant. So the second rule kicks in. That 5x, the derivative is 5. The second rule above is applied. Okay, let's do these 1, 2, 3. And just to be consistent, I'm going to do yx. So you see 5x, yx. So the constant first. I didn't have to, but hopefully, hoping it's easier. Okay. The second rule above is applied. So x dx means with respect to change in x. But in rule 3, I is not mentioned. And it's treated as a constant. Even though it's you and I would call a variable, but it's treated as a constant. So what you see is that according to mathematics, f of xy states that you started with two variables, that f defined based on two variables, right? Namely, x and y. But the computation of the partial derivative the computation of the partial derivative treats y as a constant because it did not change. It could have changed, but in this case it did not, because it did not actually change. The x you're assuming did change. The y you're assuming did not change. Okay, so that is to a mathematician. To the computer scientist, if you say int x, okay, int x. Let's leave it like that. You say int x, right? That clearly declared as a variable. But let's imagine that x equals 5, assume that this is the only command, the only step of code that uses x. So x is assigned 5, so it never changes. But still, to a computer scientist, this is called a variable. Even though x is assigned 5, it never changes. In fact, it's even stronger if I would put it in the first one, clearly. But still, despite the fact that x never changed, and it looks even more stronger, and its value is constant, throughout the execution of the code, constant throughout the execution of the code. Yet x is still a variable. Oops. There we go. Variable. Since it could have changed. Only in case of Java, only if you add the keyword final will this be treated as a constant. Since final prevents the value from changing. So again, it's not whether it could or can't. It's not whether it will or won't. It's whether it could or can't. But to the mathematician, it's whether it did or didn't, whether it will or it won't. Okay? Very interesting. This is subtle but important because when you're dealing with Karp's paper, or if you're dealing with complexity in general, it's going to be really important that you very clear on what's a variable and what's a constant. Trust me. I don't know if we'll get to it, but there's one particular problem in the Karp's paper that if you don't truly understand this distinction, you will come and make a wrong conclusion. Anyway, let's see if we get to it. Anyway, so this is quite important. It's in general important, but it's actually especially important in one of Karp's problems, where this notion is tested to the limit. Okay. All right, any questions on this? So that's the distinction between a constant and a variable to a mathematician versus a computer scientist. And again, it's very important. This is, okay, let's just summarize that. This is a very important consideration when performing analysis of algorithms, performing complexity analysis of algorithms. Okay, good. Ouch, sorry. Anyway, while I'm fixing this, any last questions? You always could ask. Okay, if I hear the ping, I will answer your question. All right, now let's. So now we were embarking on. We made the distinction between polynomial and not polynomial, exponential, and now we have hopefully a clearer, better understanding to which, in the context of computer science or complexity analysis, what is a constant versus a variable. Good. All right, so we're going to lead into and start discussing the P equal MP question. Okay, okay. So I always love telling over this anecdote, and if you hear me discuss P equal MP in one of my other courses, again the advanced theory course I'm teaching next semester in elective, a bunch of this discussion will appear. We go in much more depth because we have to do both the Karp and Cook paper. That's required, which we're only using it as a platform, to springboard in our discussions. But in the actual theory class, we go through and read it and go through every theorem. Anyway, the bottom line is, so you're going to hear the following anecdote, which is a true. I keep trying to figure it out. Is anecdotes automatically always true? The anecdotes I tell you are true stories. But anyway, just to be clear, I say it's a true anecdote. All right, so the anecdote about P equal MP, which I love telling over, it was my first semester teaching at the college, at Queens College, and I had a course a theory course where P equal NP was part of the discussion. So two very cute stories that occurred. One, 3 weeks. I love this. It was at Paramedical Hall where instead of the science building. So Paramedical Hall houses a lot of other departments, not necessarily computer science. So a student didn't realize that computer science also holds classes in the Paramedical Hall. Fine. So a student was sitting in my class, and I assumed I wrote his name down in attendance. We had a handwritten those years. I don't remember. Anyway, no, we transferred it. We had to transfer it to a form. Anyway, not important. The bottom line is that a student sat in the class for 3 weeks. 3 weeks. After 3 weeks of attending the class, the student raises his hand at the beginning of the next class and asks, "Professor, this is Philosophy 101, is it?" So I go, "No, I'm sorry, that's down the hall, five doors over." Anyway, the theory of computer science sounded so much philosophy. It's a true story. Anyway, but that's but the story about P equal NP that happened, which is true, is the following. I had spent that particular semester. We had spent an extreme amount of time ripping apart every nuance of P equal NP. And so on the final, I thought that half of the final should be dedicated to P equal NP. That was it turned out that particular semester. I didn't always do it. That one time, it was just the nature of the conversations in class just lent itself that we just ripped apart A to Z, and we did an extensive amount of material on the P equal NP question. So I think half the final was an essay question about P equal NP. And basically the question was the following. The question was, can P equal NP? Something like that. Does or can P equal NP? So after spending the entire semester, or at least half the semester on P equal NP, the student who attended the class wrote on the final the following. Can P equal NP? Yes, when N equals 1. He thought that it was an algebra question. Oh, gosh. I don't know. Anyway, I threw up my hands because it was a final. Yeah, it was on the final. Yes. So you wrote P equals NP when N equals 1. Yeah, as an algebra equation. Actually happened. It's a good story. As an algebra equation, it's true, but clearly, and the student had attended. You see, if the student never attended and then walked into a final cold, okay, so you didn't know what it was and you try your best. The student attended. You were thinking by osmosis, some of the material will seep into the brain, and you could say a word or two or fudge it a little bit. It was an essay. You would get partial credit. Anyway, so that's not the case. P equal NP is not let's write that, is not an algebraic equation. Okay, good. So what is it? So, okay, so the P on both sides somewhat refers to the same thing. The N modifies it, so it's not exactly the same. But if you just look at the P itself, the P on both sides of the equation referred to a class of algorithms. It's a fancy word. Class just means a set, but it means a complete set. It means everybody. Not just an arbitrary set. A complete set. A class. Well, a class has a little more involved, but that's not important. For our purposes, that's what it means. But that's what they call it. It's called a class. A class of algorithms. Sorry. That have polynomial time complexity. That's the P. The P is on both sides of the equation. So on the left, there's a P, and that's a complete class of algorithms that have polynomial time complexity, and on the right is also that. So P equals P, right? But what's the P equal NP question? Parenthetically, why do I say it's a question as opposed to saying that it's an equation? But you'll see in a second. Anyway, let's first define. So there's difference, though. The computer that's running these algorithms on the left is not the same computer that's running on the right. Another way to rephrase it, I think, is it's equivalent, it's equal, but it's probably hopefully a little easier. You could actually think of it as thinking, well, that the same computer. The question is, which programming language are you using? The one on the left is a certain type. The one on the right has more features. All right, maybe that's more confusing. All right, let's keep to the different computer version. All right. However, the computer hardware capabilities, the computer hardware on the two sides of the equation are different. Right, so officially, it's defined in terms of a Turing machine. Officially, this distinction is formulated in terms of Turing machines. On the left, P. On the left, the machine, which in Latin is automaton, or automata in plural. So the machine is a deterministic, a Turing machine, whereas, whereas here, whereas on the right, let's just copy this, not that idea. Whereas on the right, the machine is a non-deterministic Turing machine. Okay. Now, if you know what this means, great. If not, I'm going to explain it right now. For simplicity of our discussion, I'm not going to go through Turing machine. It's okay for you to think of it as our modern computer for our purposes. Again, in the theory course of next semester, I will presenting this, go through exactly what a Turing machine is and the types of varieties that were suggested to implement Turing machines. But for our purposes, if you know what Turing machine is, great. Although there's another time we need it again later, a little bit later. But if you don't know it for today's discussion or for this part of the discussion, it's okay. You just can think of a Turing machine as a computer, regular computer. But you need to know what deterministic versus non-deterministic means, and more importantly, and not more importantly, but and in addition, specifically for our semester for genetic algorithms, we need to understand how these differentiate themselves from random algorithms, from random computations. Because at some point it sounds sort of random and it's actually not. At least these aren't, but they could exist. Such a concept is discussed in computer science. Okay, so let's get through the definitions. Okay, right. Okay, so she was correct. Okay, so she pointed out correctly, which is the other question I asked, but let's get it over with since she mentioned it. The reason why I present it as a question and this is more of a presentation rather than a pure equation, is that P is a subset of NP. As you'll see in the definition below, as we're about to do, every deterministic algorithm is technically also included in the non-deterministic algorithms. So when you say, are they the same, half of it we know, and half of it is yes. Well, in other words, P is automatically in NP. The issue is NP in P, the other direction. So the only real question is whether NP is a subset of P. And if so, then P equals NP. That's one of the ways to prove, I should say, that according to discrete math, that is one of the ways to prove that two sets are the same. That two sets are the same. namely by showing that they're subsets of each other. Good. Okay, so thank you for your comments, Shu Hua. Okay, good, fine. So we said that. Let's put that out of the way. It's interesting, but it's not going to be that critical. As long as we're here, let me throw out one more thing, more historical or anecdotal, but it's interesting to know. The Clay Institute has a $1 billion prize. This is really true. Set aside, so it's not a annuity. It's actually an account with $1 million in it. It has one. I think it's in Switzerland. The account is a $1 million prize, which has been gaining interest. As to whether they have to give you the interest or not, it's not clear. I don't know the way that the prize was defined. But anyway, the Clay Institute has a $1 million prize set aside for anyone who can answer the question. That's why I say the question. For anyone who can answer the question or who can prove whether or not P equals NP. Not P equals NP. So certainly the Clay people treat it more of an, whatever. Whether or not P equals NP. Good. All right, now we can go on. So good, we got this over with. All right, so let's get to what the issue of deterministic versus non-deterministic is. See, deterministic is everything you've been doing. So to formalize it, it unfortunately confuses you because you do what you do because you know about what you're doing. You don't really think about it. You eat, but you don't. I remember when I took biology. So for 6 months, I was fixated as I was eating in my mind. The Krebs cycle and sorry, a fly just entered while I was talking. Small one. Anyway. Apologize. So for 6 months I was considering how biologically and chemistry-wise, how is eating done. But obviously I didn't enjoy food too much for 6 months. The thing is that everyone eats. I don't know how many people think about exactly scientifically what eating is. It's miraculous. It's an unbelievable process. But I wonder how many people, when they eat, actually think about what scientifically is eating, right? So that's I'm a little pedagogically. I'm a little bit. You do your programming. That turns out to be deterministic programming. But I have to define for you, even though most people don't think about what they're doing while they're doing it. Anyway, so deterministic. So deterministic programming. Algorithms / code means that for all possible inputs to your code, obviously, okay, for all possible inputs, every step of the execution is clearly specified by your code. There are no choices. Well, I gotta be careful. It's true, but not true. I have to be careful here how you interpret that phrase. It's clearly specified by the code. If you have an if statement, there's a choice, but you specify the choice. The computer doesn't have to make that decision. The programmer made all of the decisions for you ahead of time. Even though the programmer did not know what input you're going to put in, but the programmer thought about all possible situations. I mean, that's what a computer scientist should do with good code, right? You don't want that your little brother or sister hits the keyboard and then your code, crashes, right? So if you're assuming that you anticipate all possible inputs, so then your code is going to run. The programmer made all the decisions for you at each stage ahead of time. Even though not knowing what input the user will use. What data, let's say it that way, what data the user will input. Okay? So in a nutshell, is deterministic. Okay? Andrew says the following, so fixed course of action on some given point. Correct, Andrew. Yep, you can summarize it like that. All right, so that's deterministic. All right. The word all, I stress here, I'm not going to do this right now. In one case, we may bump into it. In the advanced theory course, I'm going to challenge that word all in the first sentence. It won't affect anything for this semester, so I'm not going to bother you. We'll deal with it if you're in my advanced theory course. You're going to see me challenge that, whether the word all inputs is necessary or not. All right, we'll deal with it. But for now, let's assume it, and let's make life simple, because it's not going to affect anything we need to this semester. All right. So that's deterministic. What is non-deterministic? Now, so in a summary statement, it's well, if I use what I just wrote and just change it slightly to become non-deterministic, it's not going to explain much, So what does it mean? It means that you didn't. Okay, right? Technically, right? It's just the opposite. Non-deterministic. You're not deterministic. So what that means is that non-deterministic programming entertains the possibility, which we're gonna formalize a little more in a moment. Just to get this down on paper, non-deterministic programming entertains the possibility that for some input and at some point of execution of the code, the programmer did not specify the course of action, as Andrew said. Good. Now that's a very nice phrase. Let me use that here. Did not specify the course of action, but rather relied on the computer to fill in the gaps for you, to fill in the gap, as it were, for the programmer. In essence, that's non-deterministic. This would only be meaningful if you assume, which non-deterministic does, that the computer always gets it right. Right? It's not just making suggestions, it's always making the correct suggestion. Okay? That's very important. We'll elaborate the details in a moment. All right? So deterministic, the programmer, the architect, figure out all possibilities, all steps, all conditions, and presents it in the code. So that way, whatever the user inputs, the code can handle it, and there's no GIGO, no garbage in, garbage out, right? And gives you the correct answer, or the answer that you anticipate. In other words, that you can prove or whatever. Fine. The non-deterministic programming or code is assuming that at some point the programmer did not specify the course of action personally, did not say it, but rather relied on the computer to fill in the gap for the programmer and tell me what to do. Right? X has to equal something. I can't figure it out. Computer, tell me what X should be equal to right now. And the computer somehow does it. And obviously, we have to assume, just to make it meaningful, is that the computer always gets it right. Because if the computer doesn't get it right, just because it's suggesting how to fill the gap, right, what value you should assign, what course of action you should take, right, it's only meaningful if it gets it right. All right? I should add, filling in the gap, let me leave it as this. Okay, fine. I'm going to give you specified assumptions you need to make to understand anti-determinism based on this. So it'll be more specified in a moment. But anybody have a question based on this general distinction between deterministic and non-deterministic? Okay. Well, while you're thinking, let me add one more comment, which is non-deterministic programming can be thought of as using conventional programming languages